I'd like to welcome our esteemed speaker of the evening. He is the CTO of Instaclustr. Please welcome Ben Bromhead.
Thank you very much for that, and thank you very much for those awesome trivia questions that I clearly wrote. A little bit of clarification, so Apple is actually the biggest user of Cassandra. Unfortunately, it is not a 75,000 node cluster. That is just the total number of Cassandra nodes they have. I think the largest one is around 2,000 to 3,000, but that's still pretty impressive. So today, I'm going to be talking about your first 6 months in production with Cassandra. What does that mean? Really, it's just an excuse for me to kind of warble on about Cassandra for a little bit, but hopefully structure it in such a way that you'll understand kind of what it's like to put Cassandra into production for the first time within your organization. Some of the things to keep in mind, some of the pitfalls to watch out for, and also just a general overview of the architecture as well. First of all, a little bit about Instaclustr. What we do, we're a managed service provider around Cassandra. We also do managed services around other kind of complementary technologies. So really you can think of us like a toolbox for high scalability. And we support a number of clouds, AWS, Google Cloud, Microsoft Azure, IBM Software. Anyway, there endeth the sales pitch, and we can kind of get on to some content. But yes, as I mentioned, we'll have a quick intro into Cassandra, a little bit about the architecture, some things to think about when putting it into production, designing and testing it, getting it into production, so covering all those little things that you tend to forget about when you're just focusing on the design, such as security. I mean, everyone follows the secure software development lifecycle, right? And then also the first 6 months, and really that's the meat and potatoes, and hopefully we'll cover a few real-life things we've encountered in helping our customers run Cassandra in production with the aim of, I guess, educating you and giving you a little bit about how Cassandra works, but also maybe a few things to try and avoid and avoid some of those pitfalls that people get into. Oh, there we go. So, first of all, a quick introduction to Cassandra. Cassandra is a NoSQL distributed database. It uses the Dynamo architecture under the hood. What does that mean? It means that every single node shares the same role as every other node, right? So it means that you can send a request to any node and it will be able to service it. It might need to forward that on to the node that has the data that it's responsible, that actually is responsible for that request. But generally, it's a shared nothing architecture. And the way it does that is it uses a sharding or a random sharding scheme where you can define in your data model a partition key. And Cassandra will automatically hash that and then distribute it around the cluster. This is something I could talk about for 2 or 3 hours, but we're kind of going to jump through it a little bit quickly just so we can give you an overview but not really get too much into the down into the weeds. The other great thing about Cassandra as well, I will say, is you can give it some awareness around the network topology in which you're deploying it. This is a really awesome feature because what it does is you can tell Cassandra what your network is like and how it's likely to fail. So if you think about a traditional data center is usually broken up into cages and racks, right? Within a rack, you generally have some shared infrastructure. Top of rack switch, maybe a shared UPS. If one of those things goes, that entire rack is likely to be out of commission. So with Cassandra, you can tell it, hey, these nodes actually share that same rack. They share that same failure domain. And so what that allows Cassandra to do is that it allows it to distribute replicas of your data between different racks, so that if you have a rack go down, you've still got those other replicas, even though there's multiple servers within that rack that it may have chosen, right? So it allows Cassandra to kind of operate in a way that's a little bit smarter. The other great thing about this Dynamo architecture and this particular sharding mechanism is it gives you some, I guess, linear scalability, right? So It's the ability to increase the size of your cluster or add more nodes and get more performance out of that. So for example, it's a very basic diagram here. We've got 3 nodes in our cluster, replication factor is 3, client sends a read or a write, just some arbitrary operation, and it ends up going to 100% of the nodes in the cluster because they're responsible for 100% of the data. We then add or double the size of that cluster, right? And because our replication factor within Cassandra stays the same, so we're saying, hey Cassandra, just keep 3 copies of our data, doesn't matter where. As soon as you add some capacity, what we can see is that exact same request, without changing any of the client logic, now goes to only 50% of our cluster. And because it's only going to 50% of our cluster, we've kind of got that remaining capacity to serve new requests, right? So this is what gives us that linear scalability. What does this look like from the data model perspective? Well, Cassandra tries to make things as familiar as possible. In fact, it makes a mistake of creating a language called CQL, or the Cassandra query language. And it makes a further mistake in trying to make that as close as possible as to SQL, just to confuse the heck out of everyone, right? There's nothing like designing a new database that's supposed to blow all the paradigms and then basing it off a language that everyone hates. That's a bit unfair. SQL is actually probably the best tool we have for this job, but it doesn't change the fact that it's hard to work with. Anyway, that's a bit of a digression. The Cassandra data model is often called a wide row storage engine. It's not a column-oriented storage engine. It still addresses everything based on rows or the partitions. But what you can do within Cassandra is you can tell it, or you can define a primary key of sorts, right? And that primary key defines uniqueness, but also how your data is organized throughout that cluster. And your primary key consists of 2 components. One's the partition key. This is the column of data that Cassandra will hash or feed through the sharding mechanism to determine where that piece of data lives within your cluster. That allows the clients to figure out which node owns the data that you want to do a read or a write for. So that again allows for really quick read and very quick reads and very quick writes. The other component is the clustering key. Now, under the hood, the way that Cassandra stores information on disk is using that clustering key. It actually lays out all your data in byte order, right? So it clusters it based on this clustering key component. It sounds really simple, and it is very simple. I won't lie to you, Cassandra is actually really simple, and it's very basic concepts. And by using this clustering key and laying everything out in byte order, it actually makes it very efficient or very easy for Cassandra to do range queries across that clustering key, right? So a very common use case within Cassandra is actually to make the clustering key some sort of timestamp. You then get all your data ordered out for a specific partition based on the time in which either you inserted it or the time that's associated with that timestamp. It makes it very easy to do slices and get to that kind of thing. So that very quickly covers the data model, the architecture. But probably the third thing that makes Cassandra quite special is this idea of eventual consistency. So as I mentioned before, within this dynamo architecture, Cassandra actually allows you to choose the number of replicas or the number of copies of data in which you spread across your cluster for any given particular row or record. And you can actually operate within the number of these replicas by defining what's called a consistency level. Now, a consistency level is effectively telling Cassandra how many nodes or how many replicas for this particular row of data that you should wait for in order to confirm a request. So what that means is if I say that my consistency level is 1, and I want 3 copies of my data spread across my cluster, and I send a request to a specific node, that node is only going to wait for one of the replicas to acknowledge or respond with that piece of data, right? And if you've got a replication factor of 3, there's 2 other nodes out there that has that data where that data might be consistent or it might not be consistent. But because we've said, hey, just wait for one answer, we're okay with that, that's fine. Cassandra has a few other consistency levels that make it easier to get what we call strong consistency with Cassandra. It's got this idea of what's called quorum. So quorum is essentially telling Cassandra to wait for 50% plus 1 of the replicas before it responds back to the client to confirm a result. What that means is with a replication factor of say 3, it waits for 2 out of those 3 to come back to you. If you're doing your reads and your writes at quorum every single time, you will always ensure that one of the nodes that received a write in the past is read from. And so that's kind of what Cassandra defines as strong consistency. So you're always going to catch the most recent update or the most recent write, but you can still sustain failure. You can still sustain one node going down. Or with a replication factor of 5, the quorum requirement at a minimum is 3, so you can sustain 2 nodes going down. This is actually really powerful from a development perspective because what it does is it forces you, the developer, to think about how your database fails when you're writing your queries. It forces you to treat failure as an everyday course of business. And you know, Cassandra's great for its scale out capability. It solves a couple of problems around there, but I think one of its most powerful things is it forces you to think about failure when you're developing your application. Too far away. Oh, here we go. So how do you go about working with Cassandra? How do you go about designing for this particular data model? What I've got up on this slide is generally the introduction to our data modeling 101 course, which is about 2 days. I won't go into it too much. But the very basics that I want you to take away from this is to think about how you access your data, think about how you're going to read your data from Cassandra, and work back from that. Think about the read patterns, the access patterns, and denormalize based on that. Writes in Cassandra are very cheap, they're very fast, they have low impact compared to a read in Cassandra. So think about your read pattern and work backwards from that. There we go. I'm going to have to stand really close to you guys to get this to work. So that's a little bit about design, how Cassandra works. It probably, yep, go ahead.
So you're saying that write is easier than read?
Yes.
Because read basically need to repair the, errors.
Potentially, right? Actually, the main reason why writes are so cheap in Cassandra is that actually the way that it structures and the way that it works with data on disk is it actually uses a log structured merge engine, right? So what that means is that when you write to Cassandra, first of all, it does something really good. What it does is it actually just appends that piece of data to a commit log on disk, which is just like, if you're familiar with Postgres, it's like a write-ahead log. If you're familiar with ZFS, it's like the intent log there. So what it does, first of all, is it just appends that to a commit log, and then it keeps on going. In fact, it doesn't even just append it to, well, it does append it to a commit log, but it only flushes that commit log to disk every 10 seconds by default, right? So when out of the box, Cassandra is effectively just writing to memory. Then what it does is it flushes that commit log to disk just for crash safety every 10 seconds. And the reason why it doesn't do it every single write is because generally you're also spreading that write to 2 or 3 other nodes as well, right? So we're kind of making a bet or a trade-off that only one node is going to kind of crash within that 10-second period for a given replica set. Then what it does is it not only does it flush that to disk, but it also stores a copy of that piece of data in memory in what's called a mem table, right? And that's just an in-memory representation of how Cassandra stores things on disk. And then eventually, once kind of memory fills up based on a few heuristics, it finally flushes that to disk as an SS table. When Cassandra goes to serve a read, what it actually needs to do is it needs to piece together all the row fragments from each one of those SS tables related to what you're trying to read back and send it back. So what that means, in order to answer your question, is that when you write to disk, or when you do a write in Cassandra, most likely you're only going to touch the disk twice. The first time is with that commit log flush, the second time is with that mem table flush, and that's asynchronously. So the client has long finished with that particular write request. Whereas when you go to serve a read, it needs to actually go through it needs to actually read each row fragment from each SS table on disk, right? So you can think about what that means in orders of magnitude of latency, for servicing a write versus servicing a read. And so that's why Cassandra has historically been far faster on writes than it has on reads, and that's why it's generally said that writes are cheap for that particular thing.
To follow up on that, so if you do a write, do a read immediately before 10 seconds has passed, is that data there or it's not there yet?
It is there. It's there immediately.
So when you piece it together, it's actually going to go.
Yeah. So it looks in memory as well as on disk, and the Cassandra node won't actually return to the client to confirm that that write succeeded until that goes into a mem table, right? So it'll do the commit log and then it'll do the mem table. And when I say when it does the commit log, it kind of puts it in that queue ready to get flushed to disk.
One more question. So, but you mentioned about that 10 seconds. I mean, that sounds a little bit dangerous. So what if 2 nodes will go down at that? So does it mean that Cassandra will just lose data right there? It's kind of built in that it can lose data?
So it all depends on your replication factor, right? So your replication factor is the number of nodes that receive that write when your client does it. So if you, and the default or the minimum replication factor that most people recommend with Cassandra is 3 nodes. So yes, if you have 3 nodes all go down at exactly the same time, then you will have a 10-second data loss window, right? And this is just by...
Not at the same time, during 10 seconds.
Yes, sorry.
10 seconds in human time is pretty big, but in computer time it's like eternity.
For sure.
There's so much can happen.
Yeah, definitely. The other thing to keep in mind is that we're spreading this across across multiple servers, so we're reducing that risk. I understand that yes, 10 seconds is a long time, but we can be doing this across different racks. We can be doing this across different data centers as well. But also that 10-second window is configurable. We can also configure Cassandra to use the standard fsync model that you're familiar with most databases. So you can actually tell it to flush to disk after every write as well. So really what it's going to come down to is the requirements of the system and the requirements of the application that you're supporting. And so kind of, the risk appetite that your organization has based on that particular application.
What's the trade-off on the configuration of that 10-second window? If you reduce it to, let's say, 2 seconds, what are you sacrificing?
It just means more flushes to disk. So really, this is just the defaults out of the box that Cassandra comes with. For some people, it's going to be great. For other people, it's not going to be appropriate. And that's like with most default configurations. What I might do is we'll park this conversation. We can address it afterwards, and we'll keep chewing through it. So testing your Cassandra application when going into, I guess, any production environment. Of course, we're always going to test things. That includes the database itself. one of the things you'll want to be testing is with Cassandra, particularly if this is the first time you put it into production, is to do very long load tests, particularly as close as you can get to your expected workload. Of course, that doesn't necessarily provide you with any guarantees that your actual production workload will match what you expect it to be. In fact, it quite often doesn't. But it will let you see if your data model is holding up to what you think your assumptions around it are. It's also a good idea to test the various failure policies. So how do you replace a node? What happens when a node runs out of disk space? All those kind of, I guess, common sense things that one should do when testing. One thing I will say around testing Cassandra and when designing or planning or kind of doing that data model exercise, Cassandra has a bunch of really cool features that are really dangerous to use. Particularly secondary indexes. That's probably the worst offender. Materialized views and lightweight transactions. They all have their use case, and when used properly and effectively, they can be really good. But they've also bit more people than we're seeing use them effectively, particularly secondary indexes, right? A quick reason why secondary indexes can be a little bit tricky in Cassandra. So what a secondary index allows you to do is it allows you to define an index on a non-primary key column, kind of similar to what you do in the relational world. But of course, Cassandra is a distributed database, right? And with that secondary index, it's going to be locally attached to the data that it's indexing. But of course, you're performing a lookup against a value that hasn't been partitioned in the way that your normal partitioning scheme is expecting. So what that means is if you query your secondary index and you don't qualify it with the partition key that Cassandra understands, it ends up doing a scatter-gather query across your entire cluster, right? So it sends that request to every single node in your cluster. That can be okay in small clusters. That can be okay where you don't really care too much about latency. But what it does mean is that when you go to scale your cluster and you add more nodes, you're actually increasing the number of replicas that your secondary index query has to go and hit, right? So you end up with this situation whereby you're kind of getting the performance of your queries are actually proportional or inversely proportional to the number of nodes you have. So the more nodes you have, the slower it gets. And really that's not what Cassandra's about. Materialized views also have a few hang-ups, lightweight transactions, which use Paxos to kind of bring a bit of ethnicity into the way you do things, to do compare and set operations effectively. They're really powerful, but of course they come with added overhead. And so, it's one of those things where, you really need to understand the ins and outs before using them. But, to be fair, that's kind of true of any database feature.
I was reading in the definitive guide that Apple created a SASI secondary index that enables light queries. And it sounds like that's almost never a good idea. Is there a use case where it is?
Yes. So SASI indexes are really good if you can qualify your statement with a partition key, right? So if you know the partition key, but you want to do a light query within a very wide row, that's a great use case because that's going to isolate that query to only those replicas, right? So you're still going to get that kind of linear performance guarantee. That's right. Just very quickly, the other thing to keep in mind, obviously you want to know what's going on with Cassandra. I won't go through this too much, but really it's making sure you've got the right monitoring infrastructure in place. This includes log aggregation, metrics aggregation, generating events from that and doing something meaningful with those events. Cassandra exposes everything through JMX, so a lot of all your common monitoring tools, Datadog, New Relic, Nagios, whatever you name it, can generally pull things out of JMX and stick it into whatever platform you're using. The main thing I would say is that try and use your your existing monitoring and metrics platform. One of the worst things to do, or to have to do, while you're trying to diagnose, a severity 0, severity 1 outage with your application, is to be looking at about 5 or 6 different vendor dashboards. So really focus on integrating this into your existing metrics so you get that nice single pane of glass. And of course, security, we don't need to cover this because no one cares about it. At a minimum, Cassandra comes with some interesting defaults from a security perspective. So no password authentication, no client encryption is enabled by default. So this is something before you go into production that you really need to look at. At a minimum, enable password auth, security, that kind of thing. If you're going to follow best practices, we generally recommend encrypting things at the application side. That sounds like a lot of overhead, particularly if you come from the relational world, where if you encrypt things at the application side, you lose the ability to do anything with that data except just kind of read it out. But with Cassandra, you're just treating it really as a key value, so you're not doing a ton of database side queries, you're not doing inner joins, you're not doing any of that. So it actually makes it a lot easier. It's a lot more, it lends itself to kind of doing in-app cryptography. Now onto the good things. So what does it actually look like when you finally go through all that pain of learning the Cassandra data model, wrestling with the fact that CQL is not SQL and it has a whole bunch of keywords just to confuse you. You've done all the testing, it all looks good, you've done security, you've written your Kubernetes scripts, your chef scripts, whatever the flavor of the month is at the day, it's all in production, ready to go. What does it actually look like? Well, day 0, it's usually pretty good because there's no data in there and you first start feeding it in. And generally your workload looks like what you did when you did in testing, right? So day 1 usually is pretty good. About 2 weeks later, you start to experience what Cassandra is like when you've got a decent production load against it. Now, hopefully some of your performance testing uncovered this, your long-running benchmarks uncovered it. But what we see from pretty much every one of our customers who has implemented a greenfield Cassandra project as their first time, they hit this issue. And that's about 2 weeks in. They go to run their first repair process. A bit of background, what is repair? It's an anti-entropy process that you can run manually in the background that tells Cassandra to, hey, between all the nodes, compare the data you've got on disk, and if we've kind of got any missing bits of data, let's restream that around. Let's kind of get ourselves nice and consistent. Particularly if you're using a consistency level that is not equal to the replication factor, you've got this situation where there can be nodes missing writes. So this repair process will catch things up, make things nice and consistent, bring it back up. Of course, as soon as you do that, it generates a lot of load on your cluster, because what Cassandra has to do is it has to read all the data off disk, generate what's called a Merkle tree, which is essentially a tree of hashes, and send that around. It sends it to all the replicas, it sends it to every node in the cluster. They all then compare their Merkle trees against each other, and if there's any differences, they then stream that across, and you've got to rewrite that to disk. So it's a fairly intensive operation, and it can have a significant impact on your end read latency and CPU utilization. But that's okay, because this is the first time we've put a new technology into production. And it's not like putting an established technology like MySQL or something into production where I guarantee that 2/3 of your team have done it previously in another company, so they've kind of got that knowledge in the back of their mind. So you generally will kind of come across a few teething issues, but this is true of any new technology that you go to put into production. So what is compaction, and why does it have such a big impact on the performance of our cluster? So first of all, as I explained, Cassandra is essentially like a log-structured merge tree or merge engine, that it's sometimes called. What that means is whenever Cassandra writes a data file to disk, it actually never updates it. So if you go to update a row in Cassandra, so first of all, let's say you know, I've got a table, username, and email, just a real simple table. I've got the username Ben, and I make the mistake of signing up with a horrible email address that I started in high school, some gamer tag or something. And then I finally think about getting a job, and I'm like, that doesn't look very professional. So I then go to update that, and I have ben.bromhead@gmail. So I update that, but now Cassandra has 2 emails on disk. It's got one in the original SS table that it wrote to disk eventually, and then it's got my new one. So if I was to update my email a lot of times, Cassandra's got to go through a lot of files on disk. This will slow down your reads. So what Cassandra has is it has a background process called compaction. This is something that normally happens in the background. You can control it. There are user-defined compactions, but generally there's an automatic process that you can use. And what it does is it grabs SS tables, merges them together, merges those row fragments, throws out any deleted data, and then writes a new one to disk. As you can imagine, this can be a IO-intensive process. And repair is something that generates a lot of this. So what is repair? As I mentioned before, I kind of jumped ahead on my slides here. That's all right. But what it is we essentially read through all the data on disk and exchange a Merkle tree or a tree of hashes. We compare those trees together and make sure they all match, right? Anything that doesn't match, we resend the underlying SS table that row fragment is in that the other node doesn't have. And that other node then has to recompact that all together. That's just actually my slide design, it's not being topped off. So when you have these 2 things together and you do your first repair, it can tend to generate quite a bit of load on the cluster, particularly if you use Cassandra's out-of-the-box repair tool, right? So Cassandra comes with essentially like a JMX toolkit, or I guess like a little binary that runs JMX commands against Cassandra to do certain admin operations. Repair is one of those. The default repair in Cassandra will generally kill most production clusters, right? Because what it does is it kicks off that repair across all ranges that a node is responsible for. And that doesn't have to just be the primary range, that'll be replica ranges as well. Particularly with Cassandra, if you're using, it's a feature called virtual nodes, which kind of breaks up that address space a little bit randomly within a node. It means that your node is probably going to be a replica or have a replica on every single other node. And so that'll generate repairs for every single node in your cluster. So it doesn't really separate it out. It generates quite a lot of overhead. And I think it's just a design choice that the committers to Cassandra decided would be awesome to trip new users up on. No, that's a lie. There are a number of different strategies you can use to get around this. The names are up there. You've got sequential repairs, which is the standard one. You've got parallel repairs, which tries to kind of get repairs to complete a little bit quicker. You've got incremental repairs, which actually tells Cassandra to only repair data that has changed since the last repair ran, right? So you're only repairing the delta. That's far more efficient, but there are a few kind of overheads with it as well in all range cases. And then you've also got sub-range repair. And what that is it's telling Cassandra to only repair a very small amount or a sub-range of data at the same time. And unfortunately, it's going to be a matter of you need to test what repair strategy is best for your particular use case and the way that your cluster is deployed. Generally, we recommend people either go with incremental or sub-range. Sub-range tends to be for older versions of Cassandra, but it's all going to come down to testing. The way that you monitor compactions and repairs is to have a look, and again, is to use NodeTool. This is a tool that comes with Cassandra that queries various JMX queries JMX for metrics, and also can issue commands against user JMX. The main thing to have a look at is the compaction stats. That's the number of pending compactions or the number of SS tables that Cassandra is trying to merge together. And what it will do is it will generate a queue of SS tables that it needs to merge. you want to kind of keep that queue fairly low, because if it's building up, that means that Cassandra is not keeping up with its compaction workload. It also means that your latency is probably going to be through the roof, because there's more SS tables on disk that it kind of needs to piece through in order to serve a single read. Cassandra also exposes some other statistics, particularly for repair, around its thread pool stats, so the number of threads it has active or committed to doing repairs or compactions, and also the network statistics, so how many outgoing streams it has open. A single node doing compactions can cause latency across the whole cluster. Particularly with vnodes, it can really impact the whole cluster, so it's a good idea to kind of keep those under control.
Now, is that like a design problem, architecture problem, and is that something that Cassandra is addressing? It sounds like it's
more a side effect of the fact that some features in Cassandra haven't kept up with other features in Cassandra, right? So there are really effective ways of doing repairs in Cassandra that don't cause all this problem, but they're not the default, right? So as a new user, you read the documentation and you say, hey, I've got to do repairs every 10 days to kind of keep my data consistent. So you've got to do it, you've got to use the default settings because you think, well, the defaults should be reasonable. But sometimes what you find, particularly with a fast-moving project like Cassandra, and it is quite a fast-moving project, is that quite often new features will have some impacts on other things that you normally do, but they haven't updated the defaults, or they haven't updated the other way, or the way that they do it. I would love to tell you that it's insanely user-friendly, but it's not. It's something we're working on as well at Instaclustr to kind of to help that. But it is a database that does have a few gotchas.
That notion again, sounds to me like very dangerous. Why do we need to do repairs every 10 days or 2 weeks? I mean, what is the source of the failures that repairs need to do? Is that a failures of the hardware? Is that the failures of the design of the software, or this is just the database itself is producing failures as a normal operation?
Yeah.
And if it is, then I really cannot imagine that Apple will choose it.
Yeah. So it sounds scary, but one of the things that you very quickly realize when you start to work with systems at scale, whereby you need to maintain consistency across a network, is the network is not reliable, right? Look, Cisco makes some really good switches, but packets get dropped, bits get flipped. You have situations whereby certain regions in your cloud provider have higher latency than normal, and it crosses a certain timeout threshold. I guess one of the things, what Cassandra does is it flips that notion on its head that the hardware is perfect, that the network is perfect, because they're not. Failure is actually part of every day of life, right? Particularly in a distributed environment. In fact, the more nodes you have, even if you've got something where you've got a failure rate of only 0.001%, is actually the likelihood that you will see something fail actually increases the greater your sample size is, right? And so Cassandra is an acknowledgement that in a distributed system, that is a course of everyday life. So that's why it builds so many safety mechanisms into itself in order to deal with this data. This is why it has a concept of anti-entropy repair. It has another repair mechanism called hinted handoff, where if a node goes down for whatever reason, it stores writes that are supposed to go to it and then replays it to it when it comes back up. That's why it has another safety feature called read repair, where if it detects a mismatch in data when it does do a normal query, it kicks off a background task to just share that individual mutation, right? So, I get where you're coming from. When you think about a database as the source of truth, the single record for your entire company, when you've got all these safety mechanisms, you're like, well, what's going on? Is it really that bad? Unfortunately, it is. The real world is that bad.
I cannot agree with that. I mean, there's a notion of strong consistency, for example, like HBase or others. I mean, do stuff with strong consistency and avoid at least that kind of problem.
They give you strong consistency, but they don't give you high availability. So when those network partitions occur, HBase is not available. You can't get that data. Whereas Cassandra gives you the choice using tunable consistency about whether you get a record that you've got some guarantees that it's consistent, you've got no guarantees that it's consistent, or you've got a very strong guarantee that it's consistent based on how you query that. Cool. So with regards to compaction, the other things to check as well that can impact the performance of your database. It all comes down to what we call SS tables per read, and this is what I was talking about. On the read path, Cassandra needs to look through files on disk, piece it together, and then return the answer back to you. It actually keeps a list of metrics around how many SS tables or files on disk it needs to read through or go through in order to serve that answer. So it's something to have a look at. And there's a number of different compaction strategies that will try and rearrange your data on disk in different ways so you can get kind of better performance characteristics. So day 85, 3 months in, or a little bit less than 3 months, you've solved your compaction issues, you've solved your repair issues. Things have kind of been going well. But you then start to see some kind of slightly higher than normal latency, particularly on your P99 or your P95. You start to see graphs that look a little bit like this. So your averages are great. They're like 2 milliseconds. That's awesome. But the 95th percentile is 23 milliseconds. The 99th percentile is 77 milliseconds. And you're trying to guarantee some level of quality of service to your end customer. The other thing that is really interesting that we quite often see when it comes to database performance is that I guarantee your largest customer, the customer that pays you the most amount of money, is the one that experiences your P99 performance, right? That's because they tend to put the most amount of load on your system. They put the most amount of data into your system. So they're the ones that are likely to experience those edge cases. And that's why it's so important, particularly on the latency side, to really chase lowering the latency of your P99s, P95s. In Cassandra, this quite often manifests itself as what we call large rows or large partitions. This is for a single partition, so as we're talking about that data, the data model component, you can have very wide rows in Cassandra. We're talking about hundreds of thousands. The problem is that Cassandra still also has a physical limit around the number of rows it can ostensibly have. It also has a practical limit. That practical limit is around 2 gig. It also depends on your use case, particularly on older versions of Cassandra when you go to read a portion of that row, so not even the whole row. It actually needs to read a lot more data off disk than what you're expecting. It also often ends up reading a lot of that data onto the Java heap. So I don't know how many of you are familiar with Java. Raise your hand if you're a Java developer. Okay, so we've got a few people that know about the pains of garbage collection and garbage collection tuning. One of the surefire ways to make your application really slow is to read or generate a lot of objects in Cassandra or in Java and then do nothing with them, right? What that does is it thrashes the garbage collector, puts a lot of objects into Eden, and then depending on the way you configure garbage collection, it might try and hang on to those objects. Or even if it doesn't hang on to those objects, you've suddenly got a giant hole in the JVM memory that it has to kind of purge during a garbage collection event. When the JVM does garbage collection, it pauses all the client threads, it pauses all your client application threads, and it goes through memory and clears it out. That means Cassandra is not serving any reads or writes during that time, right? So what we want to do is minimize the number of garbage collections that occur And minimizing the size of your rows is a great way to do that. There are some inefficiencies in Cassandra that are also being solved at this moment. There are a few outstanding tickets that make this performance slightly less pathological, but it's a great idea to kind of keep in the back of your mind as well. And of course, as I mentioned, it's your largest customer. It's the person that generally pays your company the most amount of money that's generating those very wide rows because they use your product the most. It could also be someone that doesn't pay you that much money, but has used it in a way that you haven't thought of yet. So how do you detect these large partitions? How do you figure out about going or seeing what's happening there? Well, it's really good. Cassandra keeps a bunch of metrics about the performance of the various reads and writes that it's performing. So what we can see here is a bit of a breakdown on your various percentiles about how long it's spending doing each write, how long it's spending doing each read, the size of the partition, and the number of cells that it's serving. So we can see here on your P99 that your read latency is around 20 milliseconds, and the partition size is quite large for the P99. But the largest partition it's seeing is, what, 11 gig. That's huge. And that can quite easily end up causing very long garbage collection pauses, and that impacts the latency that your other customers are seeing as well. The next thing to keep in mind is with Cassandra, and this is kind of tangentially related to compaction and large rows because it's all about how much data Cassandra has to read off disk. So the way that Cassandra deletes information is it uses a special marker or a special record called a tombstone. And the reason why it has this marker called a tombstone is actually deleting things from a distributed system is quite a bit harder than you actually think. What you have to do in a distributed system is you actually need to record the intent to delete something. Because, for example, what happens if you perform this delete, but one of the replicas for that record that you were trying to delete is down. You've taken it down to upgrade some software. You've taken it down to patch the operating system. There was a temporary network glitch. Well, what happens is that node comes back up. It's missed that delete, right? And so all of a sudden, when you go to then perform a read from it, and you think you've deleted some data, that node is saying, hey, I've got the data and it's missed that delete completely. So that's why we need to have this idea of a tombstone, because what we can do is we can say, hey, we need to delete data from this timestamp forward. We write that delete, and when that new node comes back up, we can use Cassandra's consistency mechanisms, hinted handoff, read repair, to actually redistribute that tombstone to that node, and it will no longer say, hey, I've got some data. Or even if it does say, hey, I've got some data, the coordinator node for that request will say, well, hey, I see a tombstone that has a later write timestamp than what you've got, so I can safely ignore that, right? So it's all about safely distributing deletes. If you're doing a lot of deletes in Cassandra, well, what that can mean is that you can read a row that you think might only have, say, 3 or 4 values. It can be really small. It can be a total. It can be, maybe a few bytes, the size of it. But if you've been constantly deleting and recreating that row, Cassandra actually possibly has to kind of go through thousands of deleted tombstones or thousands of tombstones on disk to figure out exactly what's going on with that particular record, right? So this is why it's really important with Cassandra to actually think about how you're doing deletes and how your compaction strategy can keep up with those deletes. Again, this is a topic that we could spend hours and hours going on about, but it's just something to keep in the back of your mind when you're doing that data model work and when you're looking at performance in production. So what does that look on a cluster that's actually going through this? Well, Cassandra keeps some great metrics around the number of tombstones it actually sees on a per read basis, and this is the maximum amount of tombstones. This is actually not a bad case. 700 tombstones for a given partition might be okay. If your latency appetite is okay with going through that number of tombstones, that could be fine, but it might be terrible and it might be impacting your end latency. So again, it's something to keep in the back of your mind. Here we go. We're almost at 6 months. You've made it through. Oh, sorry.
So related to that, is TTLs, how do TTLs tie back to tombstones?
Right, so a TTL is effectively a tombstone that is inserted at write time for you by the database. Right, so TTLs don't have quite the same problem with that the distributed delete problem, because you define a TTL, or sorry, at least default TTL. So if you define a TTL on a table, every node knows about that TTL, so it's not really a distributed delete problem. But the way that it actually implements it under the disk is it does insert a tombstone marker. But you don't generally have to worry about heaps and heaps of tombstones with TTLs, because you're generally not going to delete something. You're just going to let the TTL deal with it.
Is that part of the same process? It'll just get swept up?
Yeah, it all gets swept up in compaction. Yeah. And in fact, there's specialized compaction strategies that can deal with tables that have TTL, so it can be very efficient at deleting that data off disk.
How does Cassandra treating the node which is going down? I would assume that if node goes down, then all the data, should be deemed lost, and internal system has to propagate whatever, first or second copy to create third copy on some other nodes. And this is how the clustering, for example, in Hadoop works. Why are you saying that those tombstones are needed to restore or know what's happening if all of a sudden it comes up? If the node comes up after it went down, it should be lost completely. It can restore,
So what you're saying is, after a half a second network glitch, we should throw away a node?
It's not half a second. I mean, if node goes down, it doesn't go after half a second. You're saying after 10 seconds, nothing is written even in Cassandra. I mean, this is kind of like completely contradictory things to me.
Not quite. I think this is probably a discussion we should have offline. We'll get through the rest of the content. But I see where you're coming from. In the back?
I was like, say, if a node is down for a longer than the TTL time and then comes up after the compaction, if that node comes up, is it going to restore, resurrect the other thing?
No, not with the TTL. Because the TTL will either be defined on the table level, so Cassandra it'll know that all writes after a certain time will need to be deleted. But also, when you think about it, because the coordinator node generates that tombstone marker on the right, that's going to get distributed to it anyway. So the same mechanism that uses to catch that node up with new writes, it'll use it to catch that node up with tombstones. The other thing as well is, if let's say that node comes back up, the hinted handoff process to replay that tombstone hasn't finished yet, right? Because it's got a lot of data to get through, and that can happen. And you go to do a read from that row. Well, what'll happen is, hopefully you're doing your reads at a consistency level where it will also query one of the other replicas at the same time. The coordinator node will see that one of the replicas says, hey, I've got this data. That node that's missing the delete will actually have a different set of data, and that will generate what's called a read repair process, and that will say, hey, we need to restore consistency here.
But then that creates the severity level 1, because due to the latency and the high availability applications doesn't serve.
Yeah, definitely. So one
like for example, stock market or payment processing application doesn't going to work for.
Yeah, that's very true. So that's where making sure your application writes at a certain consistency level and reads at a certain consistency level, whereby you're always going to get the most recent set of data from it, right? And so what I mean by that is, when I go to write my data, I want to be ensuring that I'm getting more than 50% plus one of my replicas are covered. So let's say 2 out of 3 nodes on that write path. So I know that if I then do a read at that same quorum level, right, at that same level, is that even though there might be one other node that missed that write, that didn't get acknowledged, on the read side, one of those nodes is going to have all the up-to-date data, right? And so when you've got enough nodes that have, when you've got a node responding that's got all the up-to-date data, if there is one node that's potentially out of date, yes, it can kick off that read repair mechanism, which can impact your P99s. But again, that all comes down to the consistency level that you choose at your read and write. So yeah, look, value can impact your latencies, right? But you've got to, it's part of that I guess trade-off that you make about latency versus consistency.
I have actually, pretty hard time even to imagine how it works. Because you for example, said, on day 50, you already solved the problems of your day 14. And your problems of day 14 was those repairs. Mm-hmm. I mean, with the rate that data can get corrupted, for example, some repairs may not be even possible to do. Like, for example, one copy went, missing, and two other copies have different values. How will you repair it? The Cassandra, or any system will know that this data is corrupt fundamentally. There's no way to get any consensus of how to repair it. And then what? I mean, how did you solve that problem of day 14? I don't understand.
Yeah. So look, if you're getting values at that same level of it's so systemic, right, that you do have those inconsistencies, yeah, there's definitely going to be problems, right?
But you are in production and you have data which is lost or which is absolutely incorrect. How do you deal with that? How does somebody which put this system into production and get loose data, invalidate data, and then they're in production and data isn't ready? What should they do?
So if you're experiencing a situation whereby you've lost more replicas, if you've lost more replicas than what you have, right, which is kind of what you're getting at, you've sustained more failure.
One replica I lost. I go with default this replication factor of 3. I lost one replica, and other two, for example, were written in different times. They have different values. That's it. I lost that data. So it's not a lot has to happen in order to lose data. In your scenario, it looks like it's very easy thing. And then I'm in production, and I lost data. I don't know what to do.
So that's the difference between what's called strong consistency and weak consistency in Cassandra. So what we want to be doing is we want to be performing a write so that at least 2 out of those 3 nodes have received that write, and we want to be performing reads whereby at least 2 out of those 3 nodes have received those reads, right? What that means is that yes, you can lose that one node, but you will always be getting a node that has received the most up-to-date write.
But you're saying this is still not enough because somebody needs to go through that repair process every 2 weeks. And a lot of things can be incorrect, even with that notion.
Yeah, so the reason why we do repairs is so that if we then lose another node, and this is a different kind of loss, right? So this could be something whereby the disk is completely gone. Well, then all of a sudden we've got only one node that has that. So yes, there is risk, right? Because we can't guarantee all of our failure patterns. So it is a best effort. Yeah. So what we do is we can jump through that a little bit more at the end. So let's get into expansion. So changing the cluster, expanding the cluster. One of the things you do, or that you'll generally end up needing to do is as you're adding capacity or as your users are using Cassandra, you're adding more data into the cluster. At a point, you're going to reach that natural state whereby you need to add more capacity, or you need to replace a dead node. And there's a couple of steps that you need to do. But the main thing to remember is that when you go to do these operations, particularly expanding your cluster, is that because adding capacity to Cassandra puts additional load on your nodes because it's got to stream that existing data onto that new node, is you really want to make sure that things are 100% healthy. So everything's up, you haven't had, you've done all your repairs kind of up to date, and the things are nice and stable before adding that. So that means what you want to be doing is you want to be kind of scaling early, or scale early, scale often. And And so what are some signs and what are some things or kind of markers in which you should add new nodes? So the one that we generally say is that when disks start to become more than 70% full, that's when you want to start to look at adding new capacity. It can depend on your compaction strategy as well. Some different compaction strategies can use more disk space than others. Size T compaction, on a pathological use case, you want to keep at least 50% of your disk free, but that's kind of a very, I guess, rare edge case. And the other thing is obviously keep an idea on your own latencies and your CPU and your OS load. We've got a few tips for kind of adding new nodes. I won't go through all of them, but making good use of Cassandra's logical rack feature can be quite helpful. Replacing a dead node. So let's say you have a node that is irrevocably failed. So that means you can't get the data back off it, or you can't bring it back up, and you can't use those repair mechanisms to get it to be consistent again. So what you can do is you can start a new node and it will restream data from the existing replicas, right? And this will allow you to bring everything back up and still maintain that kind of replication factor of 3. So this kind of the 6-month journey of going through production on Cassandra. I would say there is still quite a lot to learn. We've worked with people that have been running Cassandra in production for 2 to 3 years, and they still, can face issues, and you do see the odd case whereby it can be a bit tricky. But with any new technology, once you've kind of gone through this process, you'll have a pretty good understanding of the way it performs, particularly with your application. And it does get to a point whereby you don't have to kind of touch it. You don't have to really think about it that much. And it's just a matter of keeping on top of it from a scaling perspective. So I want to thank you all for coming down, having a listen. There endeth the speech. I want to thank the crowd for those very engaging and thoughtful questions. And I'm going to hang around and we can have a bit of a better discussion afterwards.
Thank you very much. That was Ben Bromhead. And anyone have questions? Yeah, let's do it.
Actually, just deployed Cassandra, and I'm having a specific issue actually today, in which loading data from Spark, and I'm getting failures because writes are timing out, and I'm not getting enough replica response. I'm trying to figure out what to tune. Like, I'm happy to wait for forever, but I'd like to do like consistency 1, and that hasn't been working. If I did any, I can complete the write, but I feel like there's some risk.
Yeah, so the consistency level of any, it's kind of like the guaranteed data loss consistency level, because what it actually means is you're not getting it to one replica, you're actually just getting it to any one of those nodes commit log and hinted handoff plays. So there's not a lot of people that actually use it in production. When it comes to bulk loading from Spark, there's a number of configuration options in the Spark driver that aren't set by default. And one of those is actually write throttling. And so that's the throughput of writes that you're doing in, I think it's megabits per second. You've also got some tunables around the batch size in which it does that write. And you can also specify the number of, the number of concurrent writes you do. So you've got a few tunables where you can kind of reduce or back off or get Spark to be a little bit more gentle on the cluster. And hopefully you can start to write that data with the stronger consistency level.
Next question? Everybody? Okay, Ben will be here for one-on-one questions, so feel free to come on up and ask him. Thank you all for coming. Thank you, Ben.
Thanks so much. Cheers.